Second, let me share my screen. So you're all able to see my screen?
Yes, ma'am.
Okay.
Yes, ma'am.
You're able to see, right? Okay. So let's go get into the class. So as usual, we'll start with a brief recap of the lectures. So the first few lectures were based on blends and composites for this week 5, right? So lecture 30 was on microstructure in polymers, right? So polymeric materials microstructure was discussed, and then phase separation, where the Gibbs and free energy and the energy of crystallization and energy of mixing was discussed, right? And then regions in polymer blend, which was again taken from last week as well, was taken. And then there was a discussion on nucleation and growth. Okay, what is the minimum diameter required, right? And then how processing affects the microstructure, like flow induced or influenced changes in microstructure, or field assisted, like your electric field assisted microstructure changes, or your magnetic field assisted microstructure changes. These were all discussed in lecture 30, right? Are you able to recollect? Did you all go through the lectures?
Yes, ma'am.
Okay.
Yes, ma'am.
And then lecture 31 was on composites. So first, the natural composite wood was discussed, where the components of wood, cellulose and lignin was discussed. This was followed by composite, polymer composite with other materials. There was a discussion on that. And this was followed by size of reinforcement. How size of reinforcement affect the behavior, or how the ease of processing changes with the size of reinforcement were all discussed. And then there was a discussion on application, different applications, like in aerospace. So composites in aerospace, based on the National Aerospace Laboratory was discussed. And then epoxy and dismaleimide, which are used in aerospace primarily, were discussed, right? And how the number of components drastically changed when there was a shift from normal material to a composite, polymer composite, right? From 200 parts to 15 parts in one case, right? Did you all go through the lecture?
Yes, ma'am.
Yeah,
Yes, ma'am.
are you able to recollect that?
Yes, ma'am.
Yeah, there was a drastic difference in number of parts, number of components, right? Yeah. Okay. And then the agenda shifted to physicochemical, mechanical and electrical properties of polymers, basically different properties of polymers, right? So for the lecture 32 was on stress strain response, right? Where the stress strain curve was described, especially in case of an uniaxial tension, which is nothing but a static mechanical test experiment. So the brittle polymers, ductile, flexible polymers, how the stress strain response changes was discussed. And then there was a discussion on modulus, tensile strength and toughness, right? And then description of polymers based on the different stress strain curves was also done. And then lecture 33 was on additives. So a lot of additives, like additives for polymerization, that like initiators, right? Catalyst, and for processing, right? Like foaming agent, plasticizer, and for performance improvement. And then additional properties, like something that gives a flame retardant property, or something that gives color, right? And then on stabilizers, like UV stabilizers, thermal stabilizers were all discussed. And then there was a greater discussion on plasticizers, and then flame retardants and stabilizers were discussed. And then impact on the environment, how these additives, again small molecules, they have the capability to diffuse through like soil, air, and water was also discussed, right? This was followed by again a lecture on blends and composites in recycling, right? How, again, there's a complication, with respect to heterogeneity in polymer products, where, for example, a packaging was discussed where there are multiple layers, right? And each layer is made up of different type of polymer and polymer composite, right? So that really gives a challenge in recycling of polymers. So then chemical and mechanical recycling were discussed, and then polymeric materials recycled as blends and composites with biopolymers like plastic woods was discussed, right? And then, right, you're able to recollect? Are you all there?
Yes, ma'am.
Yes, ma'am.
Okay. I need some response in between because I can't see whether you are all there or not. Okay. And then lecture 35 was on physical and chemical cross-linking. So what is the purpose of a cross-linking? And then different types of cross-linking based on the type of cross-linking itself, like physical and chemical, and then based on functionality, uh, okay, how the topography changes, and then based on polymer backbone reactivity, right? Based on this dye in rubber, and then based on stimulus like thermal or photochemical kind of cross-linking and all were discussed. Then there was a discussion on covalent cross-linking, and then examples of different cross-linking linked systems like your hydrogel, covalent cross-linking, and then physical cross-linking based on hydrogen and hydrophobic interactions, and then supramolecules, right? And then cross-linking in biomacromolecules, where cross-linking for of pectin was discussed, right? So what type of cross-linking happens with what material pectin cross-links? What was discussed in the lecture? Someone remembers?
Calcium.
Yes, yes. Why does it, cross-link with calcium? What makes it, cross-link with calcium or interact with calcium?
Because pectin has COOH group.
Yes. So pectin has COH group, so carboxylic acid group, and that, interacts with this calcium. Okay. So it forms kind of egg box kind of structures, right? Where the calcium sits in between the box of the pectin, right? Are you able to recollect the diagram?
Yes, ma'am.
Yeah, okay. Okay. And then lecture 36, it was again on mechanical properties, right? So mechanical responses, different modes and properties was discussed, and then stretch ratio was discussed, and then elasticity, where linear elasticity and non-linear elasticity was also discussed, where linear elasticity rely on Hooke's law and on secondary interaction, and it is an energy spring, right? Whereas non-linear elasticity is based on segmental mobility and it is an entropic spring, right? And then uniaxial stretching in rubber, right, where the volume is constant, right? Volume is maintained constant, right? Because of the incompressibility that was discussed. And then non-linear elasticity model, Monet, Rivlin, and Neo-Hookean models were discussed, right? And then the final lecture of the
Yes.
week was on mechanical properties again. So different mechanical responses, like for static testing in case of small deformation and in case of large deformation, and then dynamic testing for viscoelasticity, and then advanced mechanics of polymers like failure or fracture mechanics, fatigue, impact, and then temperature and strain effect was discussed. And then coarse graining of macromolecular mechanism was discussed. And then time temperature superposition was also introduced, right? Okay. Now let's get into the practice assignments. Okay. Toughness in a polymer can we infer toughness from the izod impact strength or depth of indentation or area under the stress strain curve or Charpy impact strength? This is a gate question.
C, answer C, ma'am. Area under the stress strain curve.
Is it so? Are you sure?
Yes, ma'am.
Okay. Anybody else? You want to make a try?
C only, ma'am.
C only. Yes.
See, ma'am.
Yeah, you are right. You all are right. So toughness is energy absorption before failure. So it is, you can estimate it from the area under the stress strain curve of the material, right? Yeah. Next question. Question number 2. Match the additives to their respective functions. Paraphenyl diamine, trisylyl phosphate, polybutadiene rubber, talc. And the functions are flame retardant, impact modifier, nucleating agent, and anti-ozonant. One thing you can easily find out. The remaining may be tough, little tough for you, but one is very easy. What is that one and what is that function? You can just give a try. You can just give a try.
Ma'am, D, impact modifier.
Okay, impact modifier. What is it? Which one?
D, talc.
Is it talc? Is it
D is
talc?
for 1. Talc is for flame retardant.
Is it for flame retardant?
Yes.
Are you sure?
Yes.
Mm, someone else?
Butadiene, butadiene rubber is for impact modifying.
Butadiene rubber is for impact modifier. Okay. I'm still not saying you're right or wrong. Okay. Let's see how others
A,
also think.
A is 4 and B is 3.
These three.
A4, B3, C2, D1.
Is it so? Remaining people? Do you agree with Mr. Pramod? Or you want to take some other try? He is partially correct and partially wrong. I'm giving one more clue to all of you. So which might be correct? Anybody wants to take a guess? Someone wants to try? What do you think of rubber?
Anti-ozonant.
Is it anti-ozonant? Does it prevent ozone?
No, no, ma'am.
Rubber is impact modifier. I think it is correct.
Yes, yes. So, as Mr. Pramod said, and now Sandhya also told, right? It is an impact modifier. Polybutadiene rubber is an impact modifier. Whenever you just think of rubber, just imagine putting an impact on it and having some other material in front of it. It will take the impact, right? For example, your car bumper and all, right?
Ah, yes, ma'am.
Yeah. So that is an impact modifier. What about the rest?
Trisylyl phosphate anti-ozonant, ma'am.
Is it anti-ozonant? Someone wants to take any other guess? Or shall I say the answer? Okay, let me say the answer. So this paraphenylene diamine, this is again an anti-ozonant. Okay, and then triacylyl phosphate. So this phosphate kind of compounds you will get in flame retardant. And then polybutadiene rubber, as you all said, it's an impact modifier. Talc is a nucleating agent. Okay, these materials also might have other functions, but in this set of functions, these are the functions of the additives. Okay, you're all clear? We'll go to the next
Oh,
question. Yeah.
okay,
Okay,
ma'am.
ma'am. Okay.
Okay. Okay. Now, the tensile modulus of a thermosetting polyester resin and glass fiber are 3 gigapascal and 80 gigapascal respectively. If a tensile stress of 110 megapascal is applied along the fiber direction on a continuous uniaxially aligned glass fiber reinforced thermosetting polyester composite with a fiber content of 60% by volume, the resulting strain will be, what will be the resulting strain? This is again a gate question, gate 2022 question, very recent gate question. So what is given? Someone can say what are all the information given? Hello?
Tensile modulus of polyester resin and glass fiber.
Okay. And
As
then?
mentioned, 3 gigapascal and 80 gigapascal.
Okay.
Then tensile stress is given for uniaxially aligned glass reinforced
So for the
110
entire
megapascal.
composite, the tensile stress is being given. Okay. And they
For the
have asked what is the strain actually in this case. And they have also given what is the fiber content in the composite, right?
yes, ma'am.
Okay. So how to proceed with this? Any thoughts? Let me give one more clue. You have this Hookean law, right? Stress is proportional to strain. So stress is equal to modulus into strain, right? Now how do you take this modulus? Which modulus you have to take? How you have to take?
Maybe 3 into 0.4 plus 80 into 0.6.
Okay. Do you all agree? Do you all agree? Someone else? Basu, Sandhya, Gayatri. Do you all agree with Pramod? Is it 3 into zero point 0.4 plus 80 into 0.6?
To find modulus, you need stress by strain. So it's isn't it 110 MP by strain or something?
The strain is being asked, right? Strain is the one that is being asked, right? But they have already given the modulus. But how do you account this modulus? Because this is not a simple material, but it is a composite. How do you take the modulus? Whether you take it as just 3 gigapascal or you take it as just 80 gigapascal or you take it as as Pramod said, zero point 0.4 into 3 plus zero point 0.6 into 80. What is actually zero point 0.4 and 0.6?
The composition of the blend, composition of the.
Yes, yes. Do you all agree? It is the composition of the blend. They have given the volumetric composition, right? 60% by volume is a fiber content, right? Do you all agree?
Yes, ma'am.
Okay. So as he said, we have to take the modulus that way only. We have to use the mixing rules, simple mixing rules only, where you have to take the composition into account and their individual, uh, you know, tensile modulus, and we have to just get the total tensile modulus. Okay, that is what is given in the solution. So the tensile stress is 110 megapascal. The tensile modulus of polyester is given as 3 gigapascal. So just for the unit consistency, I am just converting it into 3 into 10 power 3 megapascal. Right? 1 gigapascal is 1000 megapascal, right?
Yes, ma'am.
Yeah. So again, tensile modulus of glass fiber is also given, and then we have the volumetric percentage of glass fiber. So you can get the volume fraction of glass fiber and also the volume fraction of resin. And then assuming Hooke's law, strain is equal to stress by total tensile modulus. So you will get, you have stress as 110 and then your total tensile modulus, which will give you approximately 2.24 into 10 power minus 3, the strain value. Okay? You're able to understand this problem?
Yes, ma'am.
Yeah, that's fine. So you know there may be the questions may be asked where the volume percent may not be given, and they would have given the stress and strain. Then in that case, what will you do? Volume fraction is not given, but they have given the stress and strain value. How will you identify what is volume fraction of each?
Strain is given for individual or for the whole one?
Well, no, strain will be given for the whole composite, right? If the strain is given for the whole composite, and then your stress is also given, and your individual modulus is given, but you have to identify what is the volume percent or volume fraction. How will you identify? Just the same question, slight modification. How will you approach that?
It will be exactly the same calculation. We can take a proportion like 1 and 1 minus x. That's it.
See, it will not be 1 and 1 minus x, it will be x and 1 minus x, because
Yes.
total volume fraction will be 1,
Yes.
total will
Yes.
be 1. So
Yeah.
1 you can assume it as x, the other one as 1 minus x, and then
Yes.
just if you substitute in the tensile modulus, you will get a equation, and also you have the stress and strain. So stress by strain is equal to modulus. So equating modulus on the both sides, you will be able to identify what is the volume percent, right? Right? Do you all agree? Hello, are you all there? You are able to get my point?
No,
Gayatri,
ma'am.
huh? You are not able to understand, is it, Vasu?
No, ma'am. No, ma'am.
See, for example, I give you the value of stress as 110 megapascal, okay? And then the strain value as 2.24 into 10 power minus 3. That is the total strain, resulting strain for the entire composite, okay? And I also give the tensile modulus of glass fiber is 80 gigapascal and your polyester resin is 3 gigapascal. Now I am asking you to identify what will be the volume percent or volume fraction of glass fiber in the composite. Right, so that I am asking you. So you know that volume fraction, the total volume, the total volume fraction you can take it as 1. And in case of x, the volume fraction you can assume it as x in case of glass fiber, and the remaining will be, you have some volume, say for example 100 ml, if 30 ml is, but you don't know what is each. So if x ml is salt, then 100 minus x ml will be your water, right? The same thing,
Yes, ma'am.
the same thing applies here also. So uh, you know uh, x will be the fraction of glass fiber and 1 minus x will be the fraction of the polyester resin. So if you just apply here, you will be changing it. Instead of here, multiplying as 0.4 into 3, you will be mentioning it as 1 minus x into 3. And here it will be x into 80. You will get some mathematical equation here where I am pointing. You are able to see. And then
Yes, ma'am.
you will have the, 10, modulus is equal to stress by strain. You know the value of stress and you know the value of strain. So 110 by 2.24 into 10 power minus 3, you will get some modulus value. That is a total tensile modulus. And you know the equation related to that. So once you equate it, simple mathematics, you can solve
Yes,
what
ma'am.
is the volume fraction, right? Yeah.
Yes, ma'am.
Yeah. You're clear, right? Okay. Now let's go on to the question number 4. Barrier height to be crossed for nucleation is a function of interfacial energy. Is it true or false? Is it true or false? Barrier height to be crossed for nucleation is a function of interfacial energy. Is it true or false? This was in the first lecture of this week, microstructures of polymers, where nucleation and growth was discussed.
It's yes, ma'am.
Are you sure? Why are you saying so?
Capital formula is my delta G, right? Delta G by RT. So delta G is function of both thermodynamics and as well as interfacial energy. So it's a function of interfacial energy.
Okay. Okay. Do you all agree with that? Are you all there?
Yes, ma'am.
Okay, you all agree with that? It is a function of interfacial energy? Or you think it is not a function of interfacial energy? Someone else wants to say anything? Okay, anyway, whoever said it is right, it's true, it's a function of interfacial energy. So, you can just see from this equation, delta GB is equal to, it is a function of cube of the interfacial energy. Okay, so whenever, the nucleus starts forming, there's a new interface created. So, obviously, for the further growth, it has to cross that interfacial energy barrier. Right? Right?
Yes, ma'am.
Do you all agree?
Yes, ma'am. Yes,
Okay,
ma'am.
fine. Fine. The major reason for amorphous nature of lignin is what is the major reason for amorphous nature of lignin? This reason was stated in the lecture. Do you remember lignin is amorphous and cellulose has crystalline units? Do you all remember that?
Yes, ma'am.
Okay, now then you can say the reason for amorphous, one of the major reasons for amorphous nature of lignin. This was also again in the lecture.
Lignin act as a matrix for cellulose.
But why
That's
should
it.
it?
That's
Why should it act as matrix? Why should it have amorphous region?
Maybe it is because of aromatic and non-aromatic combination of the structure.
Yes, you are
High
right.
molecular weight, ma'am.
It is having aromatic. So the presence of aromatic groups so makes it bulky. So restricting it from getting crystallized. Okay, that is a major reason for amorphous nature of lignin. Okay. Fine. Fine. Okay. Shivakumar, you have just joined. Okay. Shivakumar, you had asked a doubt on solving the particular problem, right, for of assignment 2. That was discussed in the previous, I think, when we were discussing the practice assignment 3, week 3 session. Hope you saw that. Okay, fine. You're able to understand the point, right? You were able to understand the solution, right? Okay, fine. That's nice. Okay. Now, the critical fiber length for load transfer is, this is in case of a polymer composite. Okay. The critical fiber length for load transfer is directly proportional to matrix ultimate shear strength and inversely proportional to fiber tensile strength, or is it directly proportional to fiber ultimate uh, tensile strength and inversely proportional to fiber diameter, or is it directly proportional to fiber diameter and inversely proportional to fiber tensile strength, or is it directly proportional to fiber diameter and inversely proportional to matrix shear strength? Which of these options are right? There was a discussion on the critical fiber length, right? And how the load gets transferred, right? So beyond a certain length only the load gets transferred properly, right? So on what factors does it depend and how does it depend? These questions are all conceptual questions. This will give you a brush up of all the concepts that you went through in the lecture. Someone wants to make an attempt? There is nothing right and wrong. If you are wrong also I am going to correct you.
The question is directly related to the elongation when we apply a load. Actually, the question is not clear. The critical fiber length means the elongation when we apply a load onto it.
See, there is a critical fiber length beyond which only there will be a proper load transfer. To estimate that critical fiber length, there is an equation. Okay. And this equation has certain parameters. So what are those parameters? Say for example, it has parameters like your diameter of the fiber and then tensile strength of fiber and all. So how is it related? Whether it is directly proportional or inversely proportional. So directly proportional means it will come in the numerator, whereas
So
inversely
it,
proportional denominator.
Directly proportional to fiber ultimate tensile strength.
I think it should be C, directly proportional to fiber diameter and inversely proportional to tensile strength.
Should it be inversely proportional to fiber tensile strength and directly to fiber diameter?
Yes.
Are you all sure? Someone said some other answer.
Directly proportional to ultimate fiber ultimate tensile strength and inversely proportional to fiber diameter.
Is it
Option
so?
B.
Someone else wants to make an attempt?
B, ma'am.
D. I mean D for
B, ma'am.
B for Bombay.
Second B.
Okay, you are also
B.
saying
Yes.
fiber ultimate strength and inversely proportional to fiber diameter. Okay, so shall I reveal the answer?
Yes,
It's
ma'am.
directly proportional to fiber diameter and inversely proportional to matrix shear strength. Okay, so this is the formula. So critical fiber length is equal to diameter of the fiber. So the smaller the diameter, the better it can take the load. And also it is directly proportional to the ultimate fiber strength. Because the more the fiber is able to take this, stress, the better is the fiber, right?
Yes, ma'am.
Yeah, that is your maximum strength before which it breaks. So it should be again directly proportional, whereas it should be inversely proportional to the matrix. Okay. Okay. Let's go on to question number 7. Brittle polymers like glassy polymers, thermosets, semi-crystalline polymers are characterized by.
Excuse me, I have some doubt on the last question.
Yeah. Tell me.
See, even if we see that shear strength is almost proportional to tensile strength, so we can say C is also equally correct.
Shear strength? No, see, here when it comes to composite with fiber,
Yeah.
in terms of fiber, you say it as tensile strength. In terms of the matrix, you say it as shear strength. When you apply a shear, matrix take it as a shear, whereas the fiber, it elongates and it takes as a tensile, elongation that is being taking place. Okay, so obviously it should depend on the uh, it should be a direct function of the diameter. So because diameter again is a direct parameter of the fiber, and again the ultimate strength of the fiber, that is the sigma uf, it is again a direct function for the fiber, whereas when it comes to matrix it is an inverse function. You are able to get it?
Yes, but still my version is that since it is not clear in the question whether it is a matrix or it is a uniform, so we can say C or D both are correct. Can we
No,
see that?
no, D you cannot say. Sorry, C you cannot say because it is directly proportional to the fiber diameter. It is
Yeah.
inversely proportional to the. It is not inversely proportional to fiber tensile strength. It is directly proportional to the fiber tensile strength. Say for example, when you have a higher tensile strength, of the fiber, then only you will be able to take a more load, right? Then how can it do? So if they are inversely proportional, then if the fiber is having more tensile strength, it cannot take more load. That is what it means, right? When you have more strength only, you can take, for example, for our case also we can say, when we have more strength only, we can lift a big 10 kg container. When we have less strength, we can lift only smaller weight, right? We can't lift a 10 kg container, right? A
Okay.
10 kg person can lift a 2 kg container, whereas a 100 kg person can lift a 15 kg container, right? It is very similar to that. So the fiber should have that tensile strength in order to bear that load, right? Are you able to get my point? Hello, Pramod?
Got it. Okay.
Got it, right?
Yeah.
You just have to immediately correlate with ourselves. So if here both are in terms of fiber. That should be directly proportional. Okay. Okay. Now let's move on to the next question. Brittle polymers like glassy polymers, thermosets, semi-crystalline polymers are they characterized by yielding or very large deformation as high as 800% deformation, or they are characterized by failure at low strains?
D, ma'am.
Huh? B. Which one? You're saying that very large deformation, is it?
No, D, both A and C.
Both A and C. You're saying it has an yielding as well as failure at low strain. How do you say so? You have to justify. Are you all agreeing with him? Or someone has any other
No, I think it should be A because sometimes thermosets, composites or thermoset polymers, they cannot get failure at even low strain. They have a very high strength as well. It may be brittle, but it doesn't mean that they will get failure or they will get crack or at a low strength.
See, this is in general scenario I am saying, not for individual cases, but general scenario. So that does thermosets have a characteristic of yielding?
Option C, failure at low strain.
Who said that?
Shweta.
Okay. It is actually failure at low strains. See, when it comes to thermosets, it doesn't have the capability of to yield. Yielding means what happens is that there will be some structural changes so that it can further take up the load and deformation, and it deforms further. Okay. But it cannot come back to its original, strain levels when the load is completely removed. Whereas in case of brittle materials, before it fails actually, if you just put a load and remove it, it can come back. So it follows complete Hookean law. Okay. But whereas once it reaches its break point, it breaks. That's it. It doesn't yield or it doesn't, there's no changes in structure. It will be like a, kind of a catastrophic break. Okay. Yielding is a property of a ductile material. Yeah, it changes in structure, and there's some microstructural changes so that it further takes up, but not as high stress as the initial part. Right? You're able to understand?
Yes, ma'am.
Yeah, if you just go through those stress strain curves, you will get it. Okay.
But
Secondary interactions.
in
Yeah.
that case, I hope the point C should not be at low strain. I think we should remove low.
See, in general scenario, this is again in general scenario, there may be case to case, some minor variation, but in general, uh, when you compare, because since there is an yielding, for example, in case of a ductile polymer, since there is an yielding, it can, it can go to further longer strains. And similarly, when you go for a rubbery material where that can take a large deformation, again, you can see that they can take up strain up to 800%. Okay, so in that general scenario, see, there might be some kind of yielding material which will fail at low strain, whereas some brittle materials which fails at a higher strain. But in general norm, if you just look into the plots, it will be that case. I think the plot is in previous page, right? One second. Okay. See, this is what is the behavior of a brittle material. Okay, whereas there is an yielding in case of a ductile material, and this rubbery material, flexible material, they take a much larger strains. You can say see the large value. This is a general, representation. Okay, Pramod, you are able to understand?
Yes, I got it.
Yeah, but in individual cases, there may be some polymer may be having, the brittle polymer itself may have a large strain, whereas the yielding one may give a smaller, where may take up a smaller strain. But this
Yes.
is the general scenario. Okay. Okay. Secondary interactions are strong with instantaneous initiation and propagation of crack in case of ductile polymers. Is it true or false? Just now we discussed brittle, ductile, flexible polymers. So is the propagation, initiation and propagation of crack instantaneous in case of ductile polymers? Someone wants to make an attempt? We just saw the plot also, the general representation plot also.
True.
Huh?
True.
You're saying true. So instantaneous initiation of crack and instantaneous initiation and propagation of crack happens in ductile polymers, and also the secondary interactions are strong. Is it? Do you all agree? Someone else wants to make a try? Okay, anyway, I'm saying the answer. It is not the case. So, the secondary interactions, okay, these are stronger in case of a brittle polymers, okay, because brittle polymers, again, your movement is all restricted
Oh, sorry, ma'am. I
and
haven't read.
their failure is catastrophic, right? So, the crack should be instantaneous in case of a brittle polymers. It is not in case of a ductile polymers. Whereas yielding and orientation happens in with large deformation. Again, the large deformation, again, it depends on the plasticity. In case of a ductile polymer, how plastic is it so that it can take a larger deformation or it fails at a lower deformation also. And then in case of flexible polymers, since there are this, the segments are itself flexible, the secondary interactions are weaker, but they can take up large deformation, and when the load is removed, they can come back. Okay, or else if the load is consistent, they may fail. Okay, for flexible polymers. Fine. Now let's go on to next question. Limiting oxygen index or critical oxygen index is given by the maximum volume percent of oxygen concentration in the mixture of nitrogen needed to support combustion of the polymer, or is it the maximum concentration of pure oxygen needed to support combustion of the polymer, or is it the minimum concentration of pure oxygen needed to support combustion of the polymer, or is it the minimum volume percent of oxygen in the mixture of nitrogen needed to support the combustion of polymer? Which one of these is right?
C.
Do you all agree?
Yes, ma'am. C option.
Okay, you're saying it is a minimum concentration of pure oxygen. Okay, but in one part it is correct, but it is not pure oxygen, but it is actually the volume percent of oxygen in the mixture of nitrogen. That is nothing but your minimum volume percent of oxygen in air needed to support the combustion of polymer. Okay, that is the limiting oxygen content. Okay, it is option D is the answer. Fine. Okay.
Yes, ma'am.
Okay. If lambda is the material time scale, then what is 1 by strain rate? This was again discussed in the lecture. I've just taken from the lecture only. Of course, it will not be in the the PDF you downloaded, but it would be in the discussion. Someone wants to make a try? Or shall I say the answer? Any try or guesses? Shweta, you want to try? Gayatri, Pramod, Vasu, Shiva? Someone wants to try?
Maybe we can say that the inverse of strain will definitely create some sensitivity to the polymer. How sensitive it is for the stress.
Uh, oh, let me give a clue. It is again a time scale. This 1 by strain rate is again a time scale. Because strain is nothing but it is your change in dimension to original dimension. So it has no unit, whereas strain rate has second inverse as the unit, right? So 1 by second inverse is nothing but seconds. So this is again a time scale. But what is this time scale? Okay, let me tell you the answer. It is nothing but your experimental time scale. So it is a time scale with which, what is the strain rate is what you give in experiments. Okay, so this is the this decides at what rate the experiment is getting carried out, and this experimental time scale and material time scale, though they play a very vital role in deciding the property of the polymer. Okay, so for example, if the material time scale and the experimental time scale are of same order, then there will be one type of behavior. Whereas if it is material time scale is higher order, whereas experimental time scale is lower order, there will be a different behavior. Whereas if the other way around, there will be a completely different behavior. This is not for different polymers, but for the same polymer, you will see different kind of behaviors. Okay, this you will really get into better understanding when your viscoelasticity properties are explained. Okay, are you able to get it? Okay, now let's move on to next question. Which of the following traits statements are true with respect to cross-linking? It induces dominant viscous behavior. It induces dominant elastic behavior. It makes the molar mass infinite, and or it makes easy recyclability of polymers.
C. Makes the molar mass infinite.
Do you all agree with that? Is it the only option?
Is it option A?
Induces viscous behavior, is it? Someone else wants to give, huh? Someone else wants to give some other try?
I think it should be C. The cross-linking makes it as a very high molecular weight.
Okay, but is it the only option that is true for this case, or there is some other option also that is true in this given set of options?
In general, A is also true and C is also true. So I do not know what we should say.
B induces dominant elastic behavior. My first preference is makes the molar mass infinite. And secondly, B.
Okay, so it is actually B and C are the right options. So it induces dominant elastic behavior. So as there is more cross-linking, again your segmental mobility and all it reduces, right? And your elastic behavior, more of a kind of a brittle nature, elastic behavior and all, it starts inducing. Okay, and also
Why
because
is it not option A? What makes option A not eligible for this one?
see, once there are more cross linking, there is there is lesser possibility of for the material to dissipate energy, right? When there is a viscous behavior, so when there is a, for example, when there is water, it is having more energy, more probability to lose or lose energy, right? Or dissipate or strain itself, right? Or deform itself. Whereas here, when there is more cross linking, for example, just imagine even water and ice also. So when it is more of a solid form, so what happens? The ability to deform gets reduced. Similarly, in case of cross-linking, what happens is that the ability to deformation is restricted by the cross-links. So it becomes more and more solid-like and elastic behavior is induced. Similarly, as you all said, the molar mass becomes infinite because the entire thing becomes a single molecular chain and it all comes into a single molar mass. Right? You can just pass through the chain completely through the crosslinks. Okay? Are you able to get the point? Are you able to?
Then why do we do with the natural rubber? We do sulfur treatment. It is to make it more viscous, right?
No. It is to make it, more stronger. Okay, it's not to make it viscous. Cross-linking is always to improve the elastic properties or, induce more of a solid-like behavior.
Okay, ma'am.
Okay? Yeah. Okay. The type of cross-linking in cellulose is it covalent bonding or is it physical cross-linking by hydrophobic interactions or is it by supramolecular interactions or is it by hydrogen bonding? What is the type of cross-linking in cellulose?
It's B.
Is it through hydrophobic interaction?
Saturday.
B.
Is it Delhi or Bombay?
D, ma'am.
D.
D.
D for Delhi.
Yes.
Yes, it is due to hydrogen bonding. Okay, in case of cellulose. So, do you all know what is supramolecular, system? Do you remember what was discussed in supramolecular system? What happens is that even in case of the monomer chain, also they do not have covalent bonding. Okay, they are through some kind of interactions. They form a chain. Even the backbone, I'm saying. Okay. Okay, now let's move on to the next question. Non-linear elasticity is entropic in origin. Justify this statement. Why is it entropic in origin? We even just discussed in the recap also. Someone remembers? Why is it entropic in origin? Someone wants to make an attempt?
In non-linear elasticity, stress depends on value of strain.
Even in linear elasticity, it depends on strain. In fact, in linear elasticity, it's a linear function of strain, whereas in case of non-linear, it becomes non-linear equation. The equation becomes non-linear. Linear elasticity is your Hookean law. Okay, this is slightly a tricky question, but let me answer. See, in case of a cross-linked polymer networks or in case of a polymer networks, say for example, in case of a rubber also, they have this rubbery nature is because of there's a segmental mobility, right? But what happens when they are deformed? So the segment adopts a stretched conformation, right? They become more stretched. So in that stretched position, the ability of that material, after being, induced with that stretch, the ability of that material to, have different conformation is getting reduced, right? So when there is a reduction in the degrees of freedom for, freedom for changing the conformation, then obviously your entropy is reduced. That means your entropy plays a vital role in case of a non-linear elasticity. Okay. Whereas in case of a linear elasticity, it's more of the secondary interactions. Okay, since the segments are already frozen, and in that case, there is a energy required. Okay, to cause to cause some strain, and that strain energy is stored as a elastic strain and elastic strain energy, and that is of where in that case there is a internal energy that is getting converted to a elastic strain energy that is being stored. Okay, and when it comes to original position, it is released. So that is of a enthalpic origin. That means in case of a non-linear elasticity, entropy term plays a critical role, since there is a reduction in the possible conformations, whereas in case of linear elasticity, it becomes more of a enthalpic spring. Okay, you are able to get my point, or you
Yes,
are
ma'am.
able you are able to understand, right?
Yes, ma'am.
Yes, ma'am.
Okay, fine, fine. It's nice. Okay, the non-linear elastic response is due to which of the following for each of the case. Say, for example, in semi-crystalline polymers at high temperature, what is the reason for the non-linear elastic response? What is the reason for non-linear elastic response for a semi-crystalline polymer? What is the non-linear elastic response? What is the reason for non-linear elastic response for a polyethylene polypropylene blend? And what is the reason for non-linear elastic response for a cross-linked rubber? This is again taken from your lecture only. I think lecture number 36. This was given in some green box where the coarse graining was discussed. If you had gone through that, you will be able to answer. You want to make an attempt, or shall I say the answer?
C, cross-linked rubber.
No. I'm asking what is the reason for cross-linked rubber to all the three materials. They will have some non-linear elastic response. I'm asking what will be the reason for each of these materials.
Okay. Maybe for C, it is like a very high molecular weight.
No, it is there in the question itself. Your answer is there in the question itself. For all the three, the answer is there in the question itself. So shall I say the answers? Shall I say? Okay, let me say. For semicrystalline polymers at high temperature, it is due to the crystalline domain. So that is what it restricts. Okay, so that ultimately results in a non-linear elastic response. And in case of polyethylene polypropylene blend, the polypropylene, it is having slightly comparatively bulkier group. So that polypropylene domain, it leads to a non-linear elastic response. Similarly, in cross-linked rubber, due to covalent cross-link. Okay. Okay. Now let's go on to the final question. Match the following: deformation till breaking, dynamic testing, large deformation, and damage in material due to repeated loading. These matches to what are which of these things? Elasticity for elastomeric polymers, fatigue, impact, viscoelasticity, fracture mechanics. What is the right match?
Deformation till breaking, fracture mechanics.
Okay.
Damage in material due to repeated loading, fatigue.
Okay.
Dynamic testing, impact. Uh,
And then
Large deformation. Elasticity for elastomeric polymer.
Okay, 3 of your answers are right, 1 is wrong.
Um,
Deformation till breaking is
Large deformation is viscoelasticity.
can I make it right?
Yeah, definitely.
Deformation till breaking is impact test. Dynamic testing is viscoelasticity. Large deformation is fracture mechanics. And then damage in material due to repeated loading is fatigue.
Again, 2 are right, 2 are wrong. Someone else wants to try? Or shall I say the answers?
Answer, ma'am.
Okay. Deformation till breaking is fracture mechanics. Okay. Dynamic testing, it reveals information on the viscoelasticity of polymers. Okay. And then large deformation, it is elasticity for elastomeric polymers and plasticity for ductile polymers. Which is this is plasticity. This portion is not given in the question, but I'm just saying in general. And then damage in material due to repeated loading. So due to continuous loading, so it need not be the breaking stress or anything. Okay, ultimate stress or anything, but some stress due to repeated loading, it may lead to a fatigue. Okay, and then deformation and energy absorption at very fast rates. So instantaneous, very fast, energy absorption and deformation rates of mechanical loading is nothing but an impact. Okay,
ठीक है.
now there was one question posted in the forum. So this was based on this reactivity ratio. Okay, the person had asked as per the given gate question. There was a gate question asked, right, for I think random copolymer. Sorry, not for random copolymer, for block copolymer. What should be the reactivity ratios, right? So where both ratios take up the same pattern, he says that it takes like a very similar pattern, both greater than 1 or less than 1. Or is there any other complementary ways also? Okay, and still the objects of alternate polymer pattern is achieved. This is what is this question. So it is possible to have all kind of combinations. So it need not be that when the reactivity of A with A is more, then reactivity of B with B should be more. It can also be like reactivity of RA can be greater than 1, where AA interaction is more, whereas AB interaction is less, while BB interaction is less with RB less than 1 with BB interaction less, whereas AB interaction or BA interaction more, implying that what does this imply is that A reacts with A and again B also reacts with B. So you will get a block of block of A with some parts of B. Again there is a randomization. Okay. So you will get some portion with B also, whereas the major portion blocks will be of A. Okay. You are able to get it?
Yes, ma'am.
Okay, fine. So that's it for the day. Thank you all. Hope this session was useful.
Yes, ma'am.
Okay. So someone asked for more questions. So is the number of questions fine? I think these are being shared. Actually, it is there in your course course page itself. It is mentioned as practice assignments or something, or live online live sessions. All the YouTube links are only one is there. I'll just check.
It's in the Excel sheet, no, ma'am.
No, it's not an Excel sheet. It will be shared. The links will be shared. I think you can download it, I guess. I didn't see how it is getting shared, but all are there. Must be there. If other things are not there, I'll just check and let you know. But I think so far, except for one, I have uploaded everything. Okay.
One we got via mail as well.
Okay. but it will get uploaded. If anything is missed, let me check and check with the team as well, so that it gets uploaded. Okay. Fine. Okay. Okay, then thank you all. Have a great evening and happy Sunday. Bye bye.
Thank you, ma'am.
Thank you, ma'am.
Thank you. Bye.